So we put 1's beside our number 1 strategy, changing to sine and cos. Okay. I'm going to put a number 2 as a second strategy beside these two because they're basically the same. It's a strategy we haven't used yet because I just introduced you to the 3 Pythagorean identities. But if you see a 1, or if you see a question that has a tan squared and a secant squared, or a sine squared and a cos squared, or a cotangent squared and a cosecant squared, they're right here up on the board. If you see that, chances are you can use one of those identities. Because there's a relationship with tan and secant, there's a relationship between cotangent and cosecant. And so those proofs allow you to do things quicker. Here's an example. You did this one. Most of you on the identities worksheet have already got probably close to, because I said you could go up to 24, right? So a lot of you have done number 16. And you did number 16 by changing to sine and cos. But I'm going to redo it now. This was the proof. Okay? Last time, you changed it to sine and cos, got a single fraction. Perfect. It works. Okay? This time, what I'm going to do is I'm going to go, hey, from factoring, do you recognize this as a difference of squares? When you have something plus something, something minus something, when I multiply or FOIL this out, I'm going to get secant squared minus 1. When I multiply that out, because it's a difference of squares. 1 is a square number, secant is a square number. And then, secant squared minus 1, I see that 1. I'm like, and I see a secant squared. Can I do that in one step to get secant squared minus 1 by itself? Yes. What's it equal to? Tan squared. Therefore, left side equals right side. No, well, what is this from? Okay, here's what's on the formula sheet. Tan squared theta plus 1 equals secant squared theta. Can you get this in mental math one step? Yeah, so then changing it to tan squared is fine. Because in mental math one step, I can move the 1 to this side, and that's what it's equal to, so I can write that down. This is a lot faster than changing to sine and cos. Okay? So related to strategy number 2 and strategy number 1, and I'm not going to give this one a number, I'm just going to put a smile face beside it. Always be aware of your goal. Do you remember that one question where I said, hey, we can change everything to cotangent. Maybe that'll make it quicker than changing to sine and cos. And when we did that, sure enough, it was quicker. Why was that a strategy? Because we looked at both sides and recognized if my other side is all in cotangent, and I can change my left side to cotangent, maybe that'll be a quicker strategy. So being aware of what you want to get on the other side can help you make those decisions. That's also true with strategy 2 using the Pythagorean identities. In this proof that I just did, I saw a tan squared and I saw a secant. And I'm like, those two are related to each other. Maybe I don't want to change to sine and cos right away, because there might be a shorter way by using how they're related. And in this case, sure enough, I didn't change it to sine and cos. I multiplied it out. Secant squared minus 1 is tan squared, and I was able to do that much quicker. So being aware of what's on both sides often is hints for a good strategy to use. Not always. Sometimes you think, oh, this is going to be a good strategy, and you try it, and it just doesn't work. And you might have to scrap it, throw it away, and say, okay, I'm going to go to sine and cos. So often what I do is I take 10 seconds to analyze my proof to say, is there a good strategy that I should try first that might be shorter? And then I try that. If it doesn't work, then I'm like, okay, change everything to sine and cos, get a single fraction. I'm going to go with the basic strategy that's going to mostly work. Now, on our strategy list, okay, I want to use an important color. Would red be red's kind of important, because like they use red for stopping, and if you don't stop, then that's bad. And stop signs are red. So I'm going to put a red star between this one, and this one, and I'm going to put not a 3, but an S. Because sometimes you're going to use the other strategies 1 and 2. You're going to get a single fraction on both sides, and they're not going to be the same, and you're going to feel like you're stuck. So the S stands for the stuck strategy. Okay? Sometimes you're going to be like, I don't know what to do. I'm stuck. Well, when you're stuck, either look if you can factor. Sometimes you won't be able to factor. And these other two are really the same thing, but one uses a word that makes it hard to remember, and the other one doesn't use words that make it hard to remember. So I'm going to often refer to it as the build the other side strategy. I'm not going to tell you what that looks like yet. We're going to run into a question that's going to have that appear. Okay, so now let's do some proofs for practice to see how these new strategies come into play. Starting off with question number 1. So how do I know if I should go to my sine and cos strategy or whether I should go to, because this one has a tangent and a secant. Can you see that? It has a cotangent and a cosecant. So you say, maybe I should use one of my tan squared plus 1 formulas or secant squared plus 1. But in this case, do you see that nothing is squared? So since nothing is squared, I would probably go back to the basic strategy of just changing everything to sine and cos and seeing what happens. So cotangent, cos theta over sine theta. Tangent, sine theta over cos theta. Cosecant, 1 over sine theta. Secant, 1 over cos theta. Multiply fractions. I have a single fraction on the right-hand side already. What would I have to do to get a single fraction on the left-hand side? I need a common denominator. How do I add fractions? Common denominator. So this one needs to be multiplied by cos and cos. This one by sine and sine. If you forget the theta, you'll get an E3 error. Why am I looking at Andre? Sorry. So we've got a common denominator. That common denominator is sine theta, cos theta. On the top, we need to add cos times cos would be cos squared. Sine times sine is sine squared. And now we've got a single fraction on both sides, but it's not completely the same. We have to do a little bit more work. Okay? And yeah, I know you see it already. A lot of you see it already, that the sine squared plus cos squared equals 1. But this is where the strategy of being aware of what's on the other side really comes up. Look, my denominators are the same. My numerator here is a 1. My numerator here is sine squared plus cos squared. Is there something I could do? Oh, how could I make sine squared plus cos squared equal to 1? Well, that's one of our Pythagorean identities, so I can just change it. And we're done. Yes? You could do that. You can change 1 to cos squared plus sine squared. You can take, in all of these equations, you can take the right-hand side and switch to the left side, or take the left-hand side and switch to the right-hand side. Yeah, just a single fraction. Now, generally, converting cos squared to sine squared to 1 seems to be more simplifying than changing 1 to something bigger. So generally, we try to write things down to 1 rather than write it as two things. So for example, if you have a secant squared, it's going to be rare that you'd want to change it to tan squared plus 1 because you're going to make that side more complicated than it was to begin with. But if you have a tan squared plus 1, you probably want to change it to a secant squared because you had two things and now you have one. And the more simple you can make something, the easier it will be to prove. Okay, I'm going to erase this one. We're going to go to B. Oh, B is scary already because B has a cotangent cubed. Okay? It also has a cosecant squared and cotangents on the other side as well. In this situation, if you change things to sine and cos, the proof is going to be long, especially with dealing with something cubed. This would be a situation where taking the 10 seconds to look at both sides and recognizing there's a relationship between cotangent and cosecant, that it might be good to use that identity. And in particular, we have cosecant squared, which is right in that identity. And here I'm going to go against what I said just 10 seconds ago and be a really good hypocrite. This is a situation where it actually makes sense to change that cosecant squared to cotangent squared plus 1. Why? Because then can you see that both sides of my proof will have only cotangents. So here we have the rare situation where it actually makes sense to replace a cosecant squared with cotangent squared theta minus 1. Now this side is only in cotangents. Can you see that you can distribute? We get our cotangent cubed theta minus cotangent theta. Or is it cotangent plus 1? Sorry, I wrote down the wrong identity. Minus cotangent theta. Do we have any like terms? Yes. These will just cancel out. And we're done. I'm going to add a part C to this one. Right? A little bit scary with a cubed. A little bit more scary if I add a power of 4. Okay? Tan to the 4 theta minus secant to the 4 theta equals negative tan squared theta minus secant squared theta. Draw your line. So again, as a positive thing to notice here, we've got tan and secant together. That seems to fit with that identity. That identity works with squares. We have nothing with powers of 4. That being said, another strategy that we listed on our page was factoring, and particularly factoring differences of squares. First of all, when you learn something mathematically and it's given a name for a reason, okay? And that reason is to help you remember it so that when you see it in new situations, like this is a difference of squared. Something squared something squared and a minus sign in between, right? That's your typical difference of squares that you saw in grade 10 and grade 11. And difference of squares are nice because they factor to be x plus something, x minus something. Why? Because when you FOIL this out, my outside's minus 3x, my inside's plus 3x, that all cancels out, and then you're left with only two terms. So by having that strong in your mind and having, like, I have a great understanding what a difference of squares is and how it's factored, because I need to be able to recognize the left-hand side here is tan to the 4 is tan squared times tan squared. And sine to the 4 is sine squared times sine squared. Or secant to the 4 is secant squared times secant to the 4. And so I can factor this to tan squared theta plus secant, plus secant squared theta and tan squared theta minus secant squared theta. And of those two factored ones, because I've factored it now, can you see which one matches up with our formula? Can you rearrange your formula to get either tan squared plus secant squared, or can you rearrange your formula to get tan squared minus secant squared? Because this is going to make a difference in what you do next. Only one of those two factors can be a rearranged version of the formula. The minus one. Can you see that there's no way that you could get tan squared plus secant squared? Like if I move the secant squared over to the other side, well, there's a positive tan squared and a negative secant squared. So by doing that little bit of mental math rearrangement, tell me I need to work with this one. So I'm going to rewrite this one, tan squared theta plus secant squared theta. And I'm going to replace the secant squared theta with tan squared theta plus 1. Okay, now I've got tan squared plus secant squared. If I distribute this negative, and you see that tan squared minus tan squared is going to go away. And a negative times the positive 1 is just going to give you a negative 1. Going directly from here to here would be 2 mental math steps and not enough work shown. But now that I have that negative out in front, I can distribute that negative, which will give me negative tan squared theta minus secant squared theta. And now that these proofs are getting more complicated, writing that QED at the end becomes even more enjoyable, because it seems like a bigger accomplishment in the proof. And so the level of difficulty of this one increases because you have to use a strategy that's not used as often, which was factoring a difference of squares. And anytime you factor, factoring makes something simplified, which makes your proof easier. If you change this to sine and cos at the very beginning, because you're like, oh, I'm only going to use that strategy, this proof is over a page long, and you still have to use factoring a difference of squares, but at a much different time in a harder to see moment. Okay? So if I wanted to make this proof harder for you, I take that away and write the right-hand side with sine and cos to tempt you to change to sine and cos right away. You still should factor first, recognize the difference of squares first to make your life easier, and then at this moment you would change things to sine and cos to finish this proof. But if I put the proof like this to begin with, you would be tempted right at the beginning to change to sine and cos. And then this proof gets really long and really hard. So these things sometimes happen on a proof. If you want the more difficult ones, things can be put in place to tempt you into a strategy that would take longer. Okay, questions for practice from your textbook, but we're not going to work on those right now, are 3, 5. Well, I guess bell's about to ring, so yes, you can work on them right now. 7II and 9II.